Hi, this presentation is part of a wider Copernicus user uptake strategy of the European Commission. One of the aims of that strategy is to stimulate the development and use of innovative downstream applications that incorporate Copernicus data and services. My name is Bruce McCormack. I represent EUROGI, the European Umbrella Organization for Geographic Information. Our overall aim is to promote the widespread and effective use of geographic information. EUROGI was asked to identify a number of use cases of Copernicus which may be of interest to practitioners in the GI community. As part of this user uptake initiative, we provide 5 case studies relating to identifying urban housing densities, land cover mapping, the spread of fertilizer on farm fields, the identification of chlorophyll and turbidity in near-coast waters, and this one, which focuses on wildfire mapping. The GIS community is without doubt one of the communities which can benefit greatly from the wider take-up of the full, free, and open data which Copernicus provides. In this module, I'll show you how Mellon Technology, an Irish GIS small SME, has used Sentinel-2 data to map the location of wildfires in Greece. The basic presentation was prepared by Calvin McCoy of Mellon Technology. Let's start with some of the problems. Firstly, out-of-control wildfires can cause extreme long-term damage to the environment, to wildlife, flora, and to property, including forestry and agricultural holdings. Also, along with improving the detection of and response times to such wildfires, there is also a need to improve post-event delineation, assessment, and monitoring of the affected areas. Such post-event analyses can then feed back into strategies and policies for wildfire prevention, prediction, mitigation, and response. Also, systems for detecting wildfires and monitoring the risk of wildfire development, such as EFFIS, the European Forestry Fire Information System, and AFIS, the Advanced Fire Information System, provide excellent up-to-date information on wildfires. However, the detection of such fires by these systems is prone to inaccuracy in terms of the exact location and extents of wildfire events and burnt areas, and they tend to fail to pick up many of the smaller wildfires which occur and which impact on the environment and on local communities in the variety of ways. Using Sentinel-2 imagery to identify wildfire areas is great and has a number of important benefits, including more accurate post-event delineation of wildfire extents. Relatively smaller areas affected by wildfires can be determined and assessed. Ground surveys to determine wildfire locations and extents can often take place on difficult terrain. Using the Copernicus data can result in time and cost savings and generally be made a lot easier. Additional data can also be used in conjunction with the Copernicus-derived imagery by a variety of organizations to better assess, monitor, and respond to the areas and communities affected by such wildfires. Also, information obtained can be used to carry out risk assessments of affected and surrounding areas. Sentinel-2 data collected over time can also be used to monitor environmental recovery, especially in relation to agriculture and in forestry, where it's very important to track such updating. Data obtained from processing of Sentinel-2 imagery can be of benefit to both GIS and non-GIS users. Some users may wish to use GIS applications to overlay various other data layers, while others may simply want maps and images with location information and extents. Examples of organizations and stakeholders who may benefit include national firefighting units, police departments, environmental protection agencies, civil protection units, forestry and agricultural management organizations, national parks organizations, farmers, insurance companies, local communities, and wildfire interest groups. Quite a good list, I think you'll agree. Set out in this slide is an example of the process which can be followed to obtain and analyze Sentinel-2 imagery to produce information on wildfire burning scarring. Step 1. Use the EFFIS, as I mentioned before, European Forest Fire Information System, to roughly locate and date the wildfires in question. Step 2. Access the Sentinel hub to identify, download, and update appropriate level C1 imagery. Alternatively, one can access the data and download it from Amazon S3. You can see the web link there for the Amazon site. Step 3, use the Sentinel Snap toolbox to carry out some initial processing and define a subset for export. Step 4, export the data for import into GIS. Step 5, further process the image. For example, one can use the cloud mask to clip the data, alter the band combinations, apply appropriate histogram stretches, and apply a normalized burn ratio, or NBR, to the image. This slide gives a summary of the hardware, software, and data which is used in the example outlined in the subsequent slides. Hardware: a computer with internet access and plenty of storage space. Software: the Sentinel Snap Toolbox. A free download is available from the web, site shown in the slide. Also software: Quantum GIS, QGIS. This is the open source GIS package which can be downloaded from the website as shown on the slide. The data: Sentinel-2 Level C1 products downloadable from the Sentinel Scientific Data Hub as in SAFE format, SAFE, SAFE format. Alternatively, Sentinel-2 Level C1 products can be downloaded from the Amazon S3 site. The web link is shown there on the slide in JPG 2000 format. This includes metadata in XML format and cloud masks in GML format. Finally, administrative boundaries, vectored files can be downloaded. Now we would like to mention some of the technical issues which need to be addressed and highlight some of the possible solutions to these issues. Firstly, downloading, processing, and storage issues. Sentinel-2 files in SAFE format are very large, frequently 6 gigabytes or more, and can take a long time to download. Seriously, this could be a problem. As a consequence of their size, they can require a lot of storage space. Also, processing the files in the Snap toolbox can be a cumbersome task. A possible solution here, in this case, is that solutions are available. If you can search for and download the data in an alternative format from Amazon S3, the web link is shown there. Using the Amazon facility, individual bands can be downloaded in JPG 2000 format and merged into a multispectral image in a GIS. The image can then be served to a web-based platform such as Azimap. The link is shown there on the slide. The result is a much smaller files, much quicker processing time, and less storage is required. Another quite frequently encountered difficulty arises because of cloud cover. Cloud cover can be a major hindrance for providing accurate data on wildfires and their aftermath, especially in regions with higher levels of precipitation. ESA's cloud mask processes a useful tool for trying to reduce the effects of cloud cover on an image, especially when the image is processed. However, the cloud mask tends to miss various areas of cloud cover. This can lead to miscalculation of pixel values, especially when the multispectral image is processed to produce a normalized burn ratio, NBR, image. The cloud coverage problem is compounded when the temporal dimension is considered. Cloud cover may inhibit the acquisition of appropriate imagery of the affected area within an appropriate post-event time frame. Alternative resources may then need to be employed to acquire the necessary data to determine wildfire location, extent, etc. In this video, we are going to work through the steps set out in the PowerPoint presentation on the process of obtaining and analyzing Sentinel-2 imagery to produce information on wildfire burning. We are going to look at an example from the Eva region in Greece, which we can see here on the Google Maps just northeast of Athens. The wildfire events which we will look at occurred between mid-July and mid-August 2016. The first thing to do is to search for wildfire events on the European Forest Fire Information System, or EFFIS for short, as I've mentioned before. We can zoom in to the area of interest, which is, in this case, in the municipality of Charistos, in the Eva region of Greece. It's here showing now. We can turn on the burned areas identified by the visible infrared imaging radiometer, suite of sensors, and the moderate resolution imaging spectral radiometer sensor. We could see there are a number of burned areas identified by these two sensors, and we can use the information tool to look at some of the details of these areas. We take a closer look at some of these areas, and we look at them now. We can see that the large burned area to the south was encoded on 25th of July 2016. We can also look at the burned area to the northwest, which can be seen was recorded on the 13th of August 2016. These various burned areas identified in this municipality are the ones which we want to locate and analyze using Sentinel-2 data. To access the relevant data, we open up the Sentinel Scientific Data Hub and log in. Once logged in, we can zoom to the area of interest. Now, using the tools available, we can draw a boundary box around the area that we want to find an image for. In the search box, we can type in Sentinel-2 and then press enter. This will bring up a large number of results. So we can run an advanced search to specify a date range. We click on the Sentinel-2 mission and then scroll up to input appropriate date range. We know that we want an image from sometime after the 13th of August, so we could specify a date range from, say, 14th August until 30th of August. Once we press the enter button, a few options should come up. We can examine each image by looking at its footprint. Here we see it come up on the map, and we can also click on the eye so to see the product details. If we scroll down a little bit, we can see some information about the image. For example, the date and time of acquisition and the size of the file. The image which we are looking at is from the 29th of August, and we can see that the file size is 5.67 gigabytes. If we click on product, we can scroll down a little more and find out more information about the image. For example, pass, direction, and the processing level. Once we are happy that the image meets our requirements, we can click on the Download Product button and download the data. The process can take quite a long time, depending on the speed of your internet connection and other factors. The next step is to open the product in the Sentinel Snap toolbox. The file needs to be unzipped before it can be opened. In the toolbox, we go to the file Open Product and search for the XML file in the unzipped folder. In the window which opens, we need to specify the correct UTM zone for the area we want to look at. In this case, it is UTM 35N. At this stage, if we try to open a full RGB image, it may take quite a while to process. Ideally, what we want to do is to create a subset image, as this will massively cut down the processing time and make it far easier to export the image and open it in another GIS system. To create a subset, all the bands have to be equivalent pixel resolution. Therefore, we have to resample some of the bands, preferably to 10 meter pixel resolution. To do this, we go to Raster, Geometric, Operations, and Resampling. Under the Resampling Parameters tab, look at the option By Reference Band from Source Product. We need to choose one of the 10 meter resolution bands as a source band to resample from. We will choose band 2 here. The unsampling method can also be changed as necessary, but we will leave it as nearest for this example. We can run the process now, and when it's done, a temporary product will have been created in the product exporter. Next thing to do is to determine an area of interest to create a subset from. A quick way to do this is to open one of the individual bands as a grayscale image, as this process is fairly quick. Now we can zoom to our area of interest. When we are satisfied that it is correct, we can go to Raster and Subset. Now we can define the bands from which we want to create subsets. For our purposes, we are going to select bands 2, 3, 4, 8, 11, and 12. Click OK, and this will create a temporary 6-band subset image. We can open up a color image with a far less processing time. To do this, we click on the subset product and select Open RGB Image Window. We select the bands which we want to display through each color gun and then open the image. Further processing can now be carried out in the toolbox. The image can now be exported to QGIS. We simply go to File, Export, GeoTIFF. At this point, we have a workable subset image. However, the process has taken quite a long time and taken quite a lot of storage space. If we need a few images, this process can take a very long time and create major storage problems and potentially lead to data download restriction becoming a problem. There is, however, an alternative method which we can use for accessing and downloading Sentinel-2 data, which circumvents many of these problems and inconveniences. We can download the data in JPG 2000 or JP2 format from the Amazon 3 window. We need to type in the following address. You could see it there on the screen. This brings us to the Amazon 3 site to access Sentinel-2 data. If we scroll down, we come to the Sentinel image browser. The green tiles we see are the image footprints, and we can also see that there is a bar which specifies the date range and also the cloud coverage percentage. Now we can zoom into our area of interest in Greece. We can define the date range. Since we know the image we are looking for is from the 29th of August, we can narrow the date range appropriately. We can leave the cloud coverage percentage range between 0 and 10. Now we can click on one of the tiles which has come up, and we can see that it is the same one which we downloaded from the Scientific Hub previously. Some details about the image show up. If we click on the link to the tile data, this opens a new window with the 13 Sentinel-2 bands. One of the advantages of using the Amazon S3 site is that we only have to download the bands which we want. When we click on band 2, it begins to download, and we can see that the size of the file is only 95 megabytes. The process can then be repeated for the other bands. The metadata can also be downloaded, if necessary, in XML format, and a cloud mask is also available to download in GML format. We are now ready to begin to create a multispectral image from the individual bands downloaded. We are going to use QGIS to do this. As with the process in the Sentinel Snap toolbox, we have to resample bands 11 and 12 to the same pixel resolution as the 10-meter bands. As we can see, the JP2 images are already loaded into the Layers panel in QGIS. We can double-click on one of the 10-meter bands and then go into the General tab. We can see that the number of pixels per column and per row are specified. We need to take note of these figures, as this is what we will use to resample bands 11 and 12. Now we go to Raster, Projections, Warp. We can specify the input file as band 11 and specify an appropriate output file. Note that the output file will not be in JP2 format, it will be in GeoTIFF format. Finally, we need to enable the resize function and change the values for width and height to the values noted earlier. In this case, we choose the width and the height to 10,980. This will resample the pixels in band 11 to the same size as those in the 10-meter bands. Now, we run the process and we repeat it for band 12 as well. At this stage, we need to merge all our bands into one layer to form a multispectral image. However, we have some bands in JP2 format and 2 bands in GeoTIFF format. We need to change bands 2, 3, 4, and 8 into GeoTIFF format. We can go to Raster, Miscellaneous, Merge, and then choose bands 2, 3, 4, and 8 in this order, which is very important, and then check the layer stack box, and then we can click OK. This will give us a 4-band multispectral GeoTIFF image, and we can repeat the process to merge bands 11 and 12 also, which will give us a 6-band multispectral GeoTIFF image. At this point, it is desirable to create a subset image. As discussed earlier, a subset image will cut down on future processing time and make it easier to enhance the image. We zoom into our area of interest. Again, it is the same municipality of Karastos. Once again, we are satisfied with this layer. We just right-click on the layer and then choose Save As. All we have to do now is select the option Map View Extent, and this will save a 6-band subset image of our area of interest. Now that we have our 6-band subset image, our aim is ultimately to try to manipulate the image in such a way that the features which we are looking for, in other words, the burned areas, show up as clearly as possible so that we can determine them and analyze them. We have a true color image open on the screen, and we can alter it by applying a histogram stretch to improve the visual characteristics of the image. In QGIS, there are a few predefined histogram stretches that can be applied, such as cumulative cut stretch or a local histogram stretch. We can also manually change the histograms for individual bands, and this is a useful feature. But for now, we will just apply a cumulative cut stretch to our true color image. Already the image appears far more visually appealing and offers more information. If we look closely, we can already make out some of the suspected burned areas. They appear to be showing up as a shade of grey or brown, as we can see here. If we recall from our EFFIS system, there should be a burned area from the last 2 months or so in this region. We can just about make them out here, a large area in the south and one more area in the northeast. 2 shortwave infrared bands can be very useful for picking up burned areas. We are going to apply a band combination of Sentinel band 12, which is a shortwave infrared band centered around a frequency of 2.19 micrometers, displayed through the red color gun, the near-infrared band displayed through the green color gun, and the green band displayed through the blue color gun. If we apply a suitable histogram stretch to the resulting image, then we can see all the burned areas showing up very clearly. They are all showing up as very distinct shades of red. Already we have some useful and accurate information on the extent and location of the burned areas. One thing to note at this point is that there are some areas which are obscured by cloud and partially obscured by cloud shadow in the map. For example, if we look at the large burned area to the south, we can see that there is some cloud cover and shadow which obscures part of the burned area. If we wish to do any further processing of the image at this stage, we can run the risk of misclassifying those areas and adversely affecting some of the data which we have produced. One way of dealing with the cloud cover is to try to remove the clouds from the image using the ESA, European Space Agency, cloud mask provided in GML format with Sentinel-2 Level 1C products. GIS will open GML files. When we have loaded the cloud mask and projected it appropriately, we can see the clouds picked out by the mask. For example, it picks out the cloud we were previously examining around the burned area in the south. However, we can also notice that there are various clouds not picked up by the cloud mask, and neither are there shadows. This is obviously an issue for the accuracy and extent of the process of masking out clouds. Various other algorithms for identifying clouds could be developed and applied to the image. For the purpose of this example, we continue using the ESA cloud mask to clip the image. It may also be desirable to mask out the water area from the image. We can use a vector file of the administrative boundaries to do this, and we can remove the clouds from the new mask. To do this, we go to Vector, Geoprocessing Tools, Difference. We can define the administrative boundaries as an input layer and the cloud mask as the difference layer. We could see the result once the process has been run. The clouds have been removed from the boundaries layer. Now, finally, we could see this layer to clip the raster image, removing the water areas and clouds identified by the ESA mask, all in one go. We go to raster, then extraction, then clipper. We specify the appropriate input file and output file, and then select mask layer, and then choose the new administrative boundaries layer. We can see that the result of this process is an image with the sea and the cloud removed. Finally, for now, we can apply a normalized burn ratio to the image. This is a formula which can potentially help to identify burned areas in a multispectral image. In QGIS, we can apply this ratio by opening the raster calculator and inputting the formula. The formula for the normalized burn ratio for Sentinel-2 is in the near infrared band 8 minus the shortwave infrared band 12 divided by the new infrared band 8 plus the shortwave infrared band 12. The result is a single band grayscale ratio image with pixel values ranging somewhere between -1 and +1. The burned areas are clearly darker than the most of the other areas in the image, and therefore we should expect a pixel value to be lower. We can use the identified tool to get an idea of the range of values in the burned areas. As we can see, there are many values appearing which range between about -0.2 and -0.35. We inspect other values in the image and see that they are generally higher. We could try to determine a threshold for burned areas at this stage and reclassify the image very simply based on the threshold. For this example, we are going to place all pixels with a value lower than -0.16 into one class, representing burned areas. A very simple way of doing this for visual purposes is just to go to the Style tab in the layer and select single band pseudo color rather than single band gray. Now we choose a suitable color ramp and select Classify to classify the pixels in the image into 5 classes. We can amend the values automatically used in the classes such that our lowest class includes all pixels with a value lower than -0.16. Once we've applied this, we can see that this is a very simple method for visually delineating the burned areas. They appear in red clearly, distinguishable from the surrounding areas in the image. This hopefully serves as a useful example on how burned areas can be identified and visually enhanced to serve many other purposes outlined in the initial part of this presentation. As accessing and processing Copernicus data and manipulating it in a GIS package requires an understanding of the data and tools which are available and the procedures needed to transform raw data into a useful product. I hope that this video has provided some useful insights and benefits in this regard. However, the processing outlined in the video is really only the first step in what is quite a long process aimed at maybe preventing wildfires such as the ones identified in the demonstration. Taking this step is, of course, of vital importance, and the free and open data provided by Copernicus represents a significant enabler. Finally, Urogi wishes to thank Melon Technology for providing the wildfires case studies. I hope you have enjoyed this presentation or find it most useful.